So in the last class, I discussed up to this threshold voltage of MOSFET in ideal case, which is Vt equal to minus Qd by Ci plus twice phi f. So Vt in the ideal case has two components, one required for creating the depletion layer in the semiconductor, which is this term minus Qd by Ci, and another term is required to create a strong inversion, right? Twice phi f, which is actually phi s, surface potential. So these two terms are there in the ideal case. For NMOS, N channel MOSFET, QD is negative. So minus QD by Ci is positive, and also phi f is positive. Phi f is Ei minus Ef, which is positive. So both the terms are positive. So this Vt in the ideal case is positive for N channel MOSFET. For P channel MOSFET, QD is positive because in the depletion layer there are positively ionized donor atoms. So QD is positive, so minus QD by Ci is negative, and phi f is also negative because phi f is Ei minus Ef. For P channel MOSFET, substrate is N type. So for N type substrate, Ei minus Ef is negative. Ef is actually higher than Ei. So this is negative. So both of these two terms are negative. So Vt is negative, right? Now,
Yes, sir.
okay. Now, before going to the real case, this is ideal case. We have ignored actually two effects here. So when we consider the two effects, which is the practical scenario, two more terms will be added to Vt. Okay. But before going there, just a detour, some discussion on the capacitance versus gate voltage of MOSFET. Now, in the MOSFET structure, you can understand that from the above discussion, previous discussion, actually in the MOS structure, there are two capacitances in series. One is the insulator capacitance, the oxide capacitance, which is just like a parallel plate capacitor. And the other capacitance is coming from the semiconductor capacitance, CS. Semiconductor capacitance come because in the semiconductor layer, there with the application of voltage, there is a change of charge. Remember, in the parallel plate capacitor, in the plates itself, there is no voltage drop. The voltage is actually the applied voltage, capacitor voltage is actually drops across the insulator, right? Remember, parallel plate capacitor, two plates,
Yes, sir.
one
Yes,
connected
sir.
to positive terminal, one connected to negative terminal. The plates itself, there is no drop across the plates,
No, sir.
but the drop is completely across the insulator, the dielectric. But this is different. Semiconductor, you remember that across the a portion of the semiconductor, there is some voltage drop. So in that region, corresponding to that region, there is a capacitance. That is the semiconductor capacitance, right? Both in accumulation and in depletion, or in depletion plus inversion, there is some voltage drop across the capacitor, Dhutrika, across the semiconductor. See
Semiconductor.
here, in accumulation, there is a voltage drop here, right? So there is a capacitance associated with this region, accumulation region. Similarly, depletion, there is a capacitance associated with this depletion region or this depletion inversion. Okay.
Yes,
So basically, there are two capacitances in series. One is this oxide capacitance or insulator capacitance, which is Ci, and this semiconductor capacitance. Is this semiconductor capacitance, you can understand in accumulation, the behavior of this capacitance will be different from the capacitance in the depletion, right? These two
yes, sir.
scenarios are different. So the behavior of the capacitance in the semiconductor will be different in these two scenarios, right?
Yes, sir.
So semiconductor capacitance, কোথায় গেল? Here. Semiconductor capacitance has been defined here as this. Since that is a voltage dependent capacitance. In the semiconductor region, the capacitance will change with voltage. That's why this is not a fixed capacitance. So that is why a more general equation of capacitance has to be used, dq by dv, not q by v. Q by v is applicable when capacitance is constant. Q is proportional to v, q equal to cv. C is a proportionality constant. So when capacitance is constant, that means q is a linear function of v. You can use that equation, but here q is not a linear function of v. Okay, so that's why we have to use more general form, dq by dv, or actually in this particular case dqs by d phi s. Qs is the semiconductor charge. Since we are talking about semiconductor capacitance, qs is the charge in the semiconductor and phi s is the voltage drop across the semiconductor, right?
Yes, sir.
This is the voltage drop in the semiconductor, if you remember
Yes.
here, right? Voltage drop across the semiconductor, voltage drop across the insulator, right? So that's why that has been used. Now in the accumulation, or before going there, the capacitance is measured. How the capacitance is measured? Using capacitor meter, right? So what does it do? It applies a DC bias across the capacitor, and superimposed on that, added with that, there is a AC signal. In order to measure capacitance, you have to supply an AC signal. Okay. Now uh, everywhere actually, in order to measure capacitance, that AC signal plus DC bias both has to be applied. Now in the accumulation region, what is happening in this particular case, we are talking about NMOS. So substrate is p type. Substrate p type means majority carrier is hole, so accumulation of hole will occur, right? So accumulation of hole will occur for negative gate to substrate voltage, negative gate voltage, right? So this is 0. In this direction, voltage is gate voltage. This is gate voltage. This axis is gate voltage. This axis is capacitance. Capacitance versus gate voltage.
Yes.
Okay. So for negative value of gate voltage, we have what? Accumulation, right?
Yes, sir.
So in accumulation, actually hole accumulate. So hole accumulate means uh, if you change the voltage in this negative range, if you vary the voltage, holes will uh, more holes will be accumulated, or holes will move out from that uh, semiconductor region. Either more hole will come in when the voltage becomes more negative, gate voltage becomes more negative, more holes will come in under the oxide, and when the voltage become less negative, some holes will move out from that accumulation layer, right?
Yes.
And this movement of hole can, and because of this movement of hole, with change of voltage there is change of charge, right?
Yes, sir.
dqs by d phi s. So these majority carriers, they can respond fast, they can move very fast in response to the change of voltage, which
Yes,
is
sir.
why this dqs by d phi s is large in accumulation region. Okay,
Yes.
that means cs is large. So cs is large, so cs and ci, ci is the insulator. Remember, all the capacitance were expressed in terms of per unit area. So cs and ci, they are in series. So when they are in series, one capacitor is large, cs is large, so what is the equivalent capacitance?
Sir, one of the effect of the smaller one.
F smaller, cy.
Yes.
So in this accumulation region, the capacitance is uh, almost ci. Ci is the insulator capacitance because
Yes.
cs is large. Okay, now understood this part?
Yes, sir.
So from a large negative value, if you increase the gate voltage to in this direction from left to right, at some point accumulation will be weak. Weak accumulation means only a small number of holes will be here. Okay,
Yes, sir.
so when their number of holes is small, you can understand, of course the change of uh, charge due to change of voltage will be a little bit smaller. Okay, So CS will not be that high, but still it will be high. So equivalent capacitance will graduate, will decrease slightly. Okay, understood.
Can you
CS
repeat
was
this?
very large.
Yes, sir.
This series combination is like a parallel combination of resistors, right?
Yes, sir.
So 1 ohm in parallel with 1000 ohm.
Yes, sir. It will be,
Equivalent is almost 1 ohm.
yes, sir.
But 1 ohm in
1.0001.
parallel with 100 ohm, equivalent will be slightly less than 1 ohm.
Slightly less than how can I say?
Less than হবে না? Parallel combination হলে কি হয়? Equivalent resistance increases or
হ্যাঁ,
decreases?
ওকে, ওকে, বুঝতে পেরেছি। হ্যাঁ, হ্যাঁ, স্যার, একটু কমলো, ঠিক আছে।
Slightly reduced, right?
Yes,
Or
yes,
1
হ্যাঁ।
ohm parallel with say 50 ohm, even slightly reduced, more reduced, right?
হুম,
So
হুম,
same thing is happening here. For
হুম,
weak accumulation, number of holes in the accumulation layer is smaller. Only a few holes are there. So capacitance, the change of this dq d phi, this becomes slightly smaller. So equivalent capacitance also decreases a little bit. Okay.
ওকে, স্যার।
This
Yes,
CFB is the flat band condition. That means that equilibrium condition I showed you above, where all
yes,
the
sir.
energy levels are flat. Actually, this is supposed to happen at 0 voltage, but because of some other uh, effects, actually this will happen at some negative value, negative voltage, which is called flat band voltage, VFB. Okay, so capacitance corresponding to this flat band voltage is CFB. It's not mentioned here, but as per my understanding, this CFB, when this is the case, actually there is neither accumulation nor depletion. So
Okay, sir.
CFB should correspond to CI only. In the semiconductor, there is no voltage drop. Okay, because if
Okay,
you remember, voltage drop is associated with bend or in the energy level.
yes,
So
sir.
when bands are flat, there is no voltage drop in the semiconductor. So this CFB should correspond to CI only. It's not mentioned here. That's what my understanding is. So
Yes, sir.
anyway, you are increasing voltage even further. So what will happen after flat band? You will move into depletion, right?
Yes, sir.
From accumulation, you will go to flat band. So bands were bend like this. Bands were bent like this in accumulation. Gradually, you are increasing this voltage. That means this magnitude of negative voltage is decreasing. So these are going up. So these bendings are becoming smaller and smaller and smaller. At some point, you will have this,
Sir,
right?
sir, 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 when we say voltage is being increased, that means we're making it positive.
More positive, yeah.
Yes, sir.
So from large negative value to less negative value.
Yes, sir.
So this will go up. So these bands will decrease gradually, and at some value of voltage, these bands will become flat. This,
Yes, sir.
okay, that is the flat band voltage. In this case, this is 0 volt, but actually, because of some, as I told you, other effects, VFB will be some negative voltage. Okay,
Okay, sir.
those effects I will discuss later. Okay, those real effects. So if you keep increasing V even more, then V becomes positive. So now the bands will be in like this. The bands will go even higher, right?
Yes, sir.
So from accumulation, you will go to flat band, then you will go to depletion, from depletion to inversion, right?
Yes, sir.
As you increase the gate voltage. So you are increasing gate voltage, so is a strong accumulation, then weak accumulation, then depletion, right? After
Yes.
depletion, of course, and in the depletion, there may be weak inversion. After weak inversion, at some point, there will be, at VT, there will be strong inversion.
Strong inversion.
Okay. So in this region, In the depletion region, this has changed. In this region, a strong accumulation and a weak accumulation. In this region, majority carriers were involved. Holes were there in the semiconductor, right?
Yes, sir.
But here, holes are no longer there. Initially, there will be creation of depletion layer. So associated with that depletion layer, there will be a capacitance, which is depletion capacitance, CD. CD is equal to epsilon S by W. Epsilon S is the permittivity of the semiconductor, silicon, since the depletion layer is in the silicon, and W is the depletion layer width. So again, this capacitance is capacitance per unit area. So that's why there is no A here. Understood?
Yes, sir.
So this is the depletion in this region and this region. This is the depletion layer capacitance, epsilon S by W. So as you are increasing V, what is changing? The W is what?
Increasing, sir.
W is increasing. So what is happening to CD?
Decreasing.
CD is decreasing. So here CD and CI are there in series. Okay, in this region.
But in the
CDCI they are
depletion
in
region,
now
sir.
CD is decreasing, so their equivalent capacitance is also
Decreasing.
decreasing.
Oh,
Okay.
yes, sir.
Now at some point at a strong inversion, what will happen? Though I told you there it will not exactly match, but to some extent it will match. Okay, inversion ideally should have been here at this minimum point, but here actually VT is shown here past the minimum point because of some other effects, as I told you. But
Yes, sir.
ideally, at this, when a strong inversion is achieved, the depletion layer width is maximum, right?
So when the so can
When
you
a strong
kindly?
inversion is achieved, the depletion
Yes, sir.
layer width is maximum,
Yes, sir.
WM.
Yes, sir.
Remember that?
Yes, sir. Yes, sir. Yes, sir.
Okay, WM, this WM, when a strong inversion is achieved. So depletion layer width is maximum, so value of CD is
So minimum.
minimum. So the equivalent capacitance is also minimum.
Is minimum. Yes, sir.
Okay,
Yes, sir.
because CD is in series with CI, right?
Yes, sir.
Equivalent capacitance is CI CD by CI plus CD. So this minimum point corresponds to this equivalent capacitance CI CD mean by CI plus CD mean. CD mean is the capacitance corresponding to WM, epsilon S by WM.
Yes,
Okay.
sir. Yes, sir.
After this point, if you keep increasing V, what will happen? Remember, this
W.
V is a DC voltage. This V is DC voltage. This
Yes,
is the
sir.
DC bias I talked about. When you are measuring gate capacitance, you have to apply a DC bias. That DC bias is this gate voltage.
Yes,
And
sir.
superimposed on that DC voltage, you have to apply a small signal AC, a small AC voltage, because you cannot measure capacitance using DC voltage. In order to measure capacitance, you have to use AC signal. Okay. So
Yes, sir.
this VG is the DC bias, and superimposed on that, there is the AC signal. Now, if the frequency of the AC signal is high, what will happen is remember here we have beyond this point, the depletion layer width is fixed. The depletion layer width is not changing. So depletion layer charge is not changing. So depletion layer has no contribution to semiconductor capacitance beyond that minimum point. Understood?
Yes, sir.
Again, at this point, depletion layer width is maximum. Okay. So depletion
Yes.
layer charge coming from ionized acceptor atoms, that becomes fixed. After this, that amount of charge minus QNAWM, that will not change.
Yes, sir.
So what will change? If you keep increasing gate voltage, the inversion layer charge will change.
ওই যে স্যার more and more charges are accumulated ওই যে আরো স্ল্যান্টিং হয় তারপরে কিন্তু আমাদের
Inversion
ডিপ্লেশন
layer
লেয়ারটা
charge
যেখানে
will
আছে ওখানে
increase.
থাকে
Yeah, but depletion layer charge will not change.
It will not change. Okay, বুঝতে
Okay,
পেরেছি, yes.
so the contribution to capacitance will come from inversion layer charge, which are electrons, minority carriers.
Okay.
Okay, so say at this, after this point, V is something, gate voltage is greater than VT. Now you are applying a AC signal. Now at the positive half of the AC signal, what will happen to the electrons?
Yes, sir.
Hmm?
Uh,
More electrons will come.
হ্যাঁ,
When the there is positive half of the AC signal, that means that is being added with the gate voltage. So gate voltage has increased positively.
yes,
So
sir.
that means the electron in the inversion layer has to increase.
Yes, sir.
How the electrons can increase?
So
They has to come through the p type substrate, which is neutral.
yes, sir.
Okay,
Yes, sir.
and when the AC signal goes to its negative peak, what will happen? Electrons from the inversion layer has to go away from the inversion layer. The gate voltage will
Alaikum sir.
gate voltage will decrease, right?
Yes, sir.
Sir, one
Do you
student is
have
in the
a DC
waiting room.
voltage? Sorry, this is
One
VG.
student,
Yes,
one student is in waiting room.
one student.
He messaging me.
Ah,
Yeah,
about what?
he's in waiting room
There is no waiting room in this
about the class.
meeting. Waiting room is disabled. There is no waiting room. Okay, this is VG. This is voltage. Sorry, this is time versus voltage, right?
Yes, sir.
Arre. So during this AC half, positive half, gate voltage is increasing. So
Yes, sir.
correspondingly, negative charge in the inversion layer should increase, right?
Yes, sir.
And in this negative half cycle, gate voltage is decreasing. Decreasing than VG, definitely. Decreasing means
Yes, sir.
compared to VG. Positive peak, voltage is increasing, compared to VG, negative peak, sorry, negative half cycle, gate voltage is decreasing. So electrons in the inversion layer should also
Decrease.
So
Yes.
electrons have to move out of the inversion layer or come into the inversion layer in response to this AC signal through the p-type semiconductor, p-type body, right?
Yes, sir.
So
Yes, sir.
electrons are minority carriers, and those require time to move in and move out of the inversion layer through the p-type body. So what
Yes, sir.
happens is, if the AC signal has high frequency, the electrons cannot follow the variation of voltage.
Okay. Okay,
Okay,
sir. Okay.
because electrons need time. As I told you, there are minority carriers. They have to go to the p-type material, recombine, or they have to be generated in the p-type material, then come to inversion layer. These things take time. So for
Yes, sir.
high frequency AC signal, if you use for capacitance measurement, the inversion layer will no longer contribute to the capacitance. So the capacitance CD will be fixed at that minimum value. Okay, which was there at the strong inversion point.
Okay, sir.
So this point. So for if you use high frequency AC signal to measure capacitance, capacitance will not change. It will remain fixed at this value.
Okay, sir.
But if you use low frequency AC signal, then what will happen is electrons now can follow the variation of voltage. So now CD is large. Again,
Yes, sir.
CD comes from the change of inversion layer charge, not from the change of depletion layer charge. Okay, now for slowly moving voltage, কি কয় আমার তো ওয়েটিং রুম তো ছিলই না এনেবল ওয়েটিং রুম ঠিকই তো আছে নাই তো করা so now CD is large. So when CD is large, what happens? CD in series with CI, So equivalent capacitance will become Ci again
Yes.
for low frequency. For high
Yes.
frequency, it will remain minimum. Here, majority carriers are involved. They can respond to a high frequency, low frequency, both frequency with ease. So there is no distinction here between high frequency, low frequency. Same.
Yes, sir.
Okay. So C versus capacitance versus gate voltage, CV characteristics, understood, of a MOS
Yes,
structure.
sir. Yes, sir.
Okay, so those are the things mentioned here. I am skipping that. Okay, low frequency, high frequency here. After inversion is reached, the small signal capacitance depends on whether the measurement is made at high or low frequency. So high frequency means in the range of 1 megahertz. Low frequency means typically 1 to 100 hertz. Okay. So if the gate voltage is varied rapidly, that means high frequency, the charge in the inversion layer cannot change in response and thus does not contribute to the small signal AC capacitance. Okay, the thing I just mentioned.
So here the charges are the negative minority carriers.
Minority carrier, electrons, yes.
Yes, sir.
Hence, the semiconductor capacitance is at a minimum corresponding to the maximum depletion width, that means WM, CD min.
Yes,
Okay.
sir.
On the other hand, if the gate bias is changed slowly, there is time for minority carriers to be generated in the bulk, drift across the depletion region into the inversion layer, or go back to the substrate and recombine. Okay, so electrons, I told you, will move in and move out from the inversion layer through the depletion layer to the substrate. Right?
Substrate is the body, sir. Right, sir.
Substrate is the body. Yeah.
Yes.
So now the semiconductor capacitance will be is very large. So CD is large now. Hence, the low frequency MOS series capacitance in a strong inversion is basically CI once again. Okay.
Yes, sir.
And here, why there is no variation for high frequency, low frequency capacitance in accumulation, that is mentioned here. We get a very high capacitance at both low and high frequency because the majority carriers in accumulation, okay, the majority carriers in the accumulation layer can respond much faster than the minority carriers.
Yes, sir.
Okay. So that is all about capacitance voltage characteristics of MOSFET. Now we'll move on to the effects of real surfaces. So this is actually related to this VT. This VT is correspond to ideal case. Now I told you we have ignored some practical scenario which we will include here. Because of that, a few terms will be added here. The basic thing is actually here, because of some effects, two effects actually there we have ignored. One is, first, there is a work function difference between metal gate and substrate. We assume that in the ideal case, Q phi m is equal to Q phi s, phi m equal to phi s. That means metal and semiconductor has equal work function. That is one assumption, right?
Yes, sir.
But in real scenario, that will not be the case. So it's obvious. So
Yes,
that
sir.
is one thing. And another thing is, I told you at the surface oxide semiconductor interface, also in the oxide layer itself, there are some things happening. There will be some additional charge in the oxide semiconductor interface and also within the oxide layer, because of which there will be some uh, consideration, okay, that which we have ignored. Those
Yes.
charges come from actually various imperfections or impurities,
Okay, sir.
which is not present in the ideal case. So because of those, that also there will be an additional term in the VT expression. So those things will be considered and we'll modify the VT expression accordingly.
Yes,
But
sir.
the thing is, because of these two, metal and semiconductor work function difference and the surface effects, surface charges, actually when you form the MOS structure, automatically there is some because of alignment, the Fermi level will of semiconductor and metal, are not at same position, so they, because of their alignment, there will be some band bending, right? And
Yes.
in order to make the bands flat again, you have to apply some additional voltage. Okay, why? That is the main thing. Why we are thinking in that way? If we go back here, remember here we started with a condition where the energy levels were flat, and in order to get this condition, actually we made that simplified assumption that phi m is equal to phi s. But when you consider those two scenario, real scenario, phi m is not equal to phi s and there are interface charge. When those things are considered, you will see when you construct the MOS structure, there will be automatically already some band bending, just like PN junction. Even if without any applied voltage, there is some band bending, right?
Yes, sir.
Because of the requirement of the alignment of Fermi levels, right? So
Yes, sir.
the first thing you have to do is to apply a suitable gate voltage which will make the bands flat again. That voltage is called flat band voltage, VFB, which I showed you in the capacitance voltage diagrams. VFB, flat band voltage. So once you have applied that flat band voltage, the bands have become flat. After that, everything is same as this scenario. Okay, you, by applying this voltage, this additional voltage, you can get accumulation. By applying this type of additional voltage, you can get depletion. By increasing this voltage, you can get inversion. Everything else is same. Okay, so the
Yes.
Sir,
main
at flat band voltage will phi m be equal to phi s?
sorry,
Sir, flat band voltage এর সময় স্যার phi m আর phi s equal হবে?
no, phi m phi is equal hobe na, but these energy bands with energy levels will become flat.
Okay, sir.
Okay, how I will show you. The requirement there is you are adding an additional voltage to make the bands flat again. Why the bands were not flat? Because of that work function difference and those surface effects. Okay,
Yes.
so that flat band voltage VFB has to be added to VT. That is the main thing. Once the
Yes,
flat
sir.
band is achieved, these things are same as this scenario. This accumulation, depletion, everything is same. Okay.
Yes, sir.
So let's see the work function difference first. Work function difference. This is the first consideration. We expect phi s to vary depending on the doping of the semiconductor, right?
Yes,
If
sir.
you vary the doping of the semiconductor, EF, the position of Fermi level, EF will vary. So obviously Q phi s will vary, right?
Yes, sir.
Yes.
Figure 617 illustrate the work function potential difference phi ms. Phi ms is phi m minus phi s for n plus polysilicon on silicon as the doping is varied. So n plus polysilicon is in the middle era. The heavily doped polysilicon was used as a substitute for gate metal. Instead of metal in the gate, uh, heavily doped polysilicon layer was used. So that's why N plus polysilicon is being shown here. So if we have a N plus polysilicon on P-type substrate, that type of uh, gate structure, that means N plus poly, then oxide, then P-type silicon, then with the variation of P-type silicon, with the variation of acceptor concentration in P-type silicon, the phi AMS get work function and semiconductor work function difference phi ms, that means phi m minus phi s. Here phi m represents the work function of n plus polysilicon. Okay, and phi s represents the work function of p type silicon. So this phi ms will become more and more negative with increasing acceptor concentration in the p type silicon, p type semiconductor. Okay, that is like this. Why? Because you can understand, if you dope p type more heavily, the semiconductor Fermi level will go down. The gap between EI and EF will increase. Understood? Or should I draw? Hello?
Sir, do you want to draw, sir?
Rosani,
If you
P-type
want, sir, you
silicon,
can.
right?
Yes, sir.
EC, EV. This is EI.
Yes, sir.
This is EF.
Yes, sir.
So if you increase doping, what will happen to this?
It will go down.
This gap EI minus EF will increase. So
Yes, sir.
somewhere here is my oxide conduction band.
Yes, sir.
This gap is Q phi S,
Yes, sir.
right?
Yes.
So what will happen to phi S?
Phi S will increase.
Phi S will increase. Okay.
Yeah.
So phi S is changing. Phi M will not change.
Okay, okay.
Phi S
sure.
is increasing.
Yes, sir.
Okay. So
ও তাহলে
phi
ওটা
MS
নেগেটিভ হতে থাকবে
phi MS will become more and more negative.
নেগেটিভ
Understood?
yes
And for N plus poly to N silicon, this kind of gate structure, that means gate is N plus poly, then oxide, then N type silicon. If you
Yes, sir.
increase doping, in this case, doping means ND. Okay, ND is
Yes,
the
sir.
doping of N type silicon. If you keep increasing doping, the phi ms will become less and less negative.
Yes, yes.
Both are negative, but this will become less and less negative, but this will become more and more negative.
Yes, sir.
Understood?
Yes, sir.
Okay. So, কোথায় গেল? Figure 617 illustrate the work function potential difference phi ms for N plus polysilicon on silicon as the doping is varied. For other metal electrodes, the work function of that metal phi m must be used. So instead of N plus poly, if you use say aluminum or gold or silver, you have to use phi m of those metals. Okay.
Yes, sir.
But typically, phi ms is always negative. Okay, we note that phi ms is always negative for this case, but also for metal gates, phi ms is negative. So we, in our all calculations, we will assume phi ms is negative, and is most negative for heavily doped p-type silicon. That means for heavily doped p-type silicon, this is very most negative. That is actually obvious from the figure. If we try to construct an equilibrium diagram with phi ms negative, we find that in aligning EF, we must include a tin tilde oxide conduction band, which implies an electric field. So I have drawn it here. Before joining metal, oxide, and semiconductor, this is the energy band diagram. This is metal with EFM. This is oxide. This is the oxide conduction band. This is the p-type semiconductor with EF close to EV. Now this Q phi S is greater than Q phi M, because phi ms is negative, I told you. Okay, we
Yes, sir.
typically phi ms is negative. That means phi m is less than phi s. So when you join these three structures, EFS and EFM will align. So when they align, that means these energies have to go up,
Yes,
right?
sir. Yes, sir.
So there will be a tilt in the oxide conduction band like this,
Yes, sir.
right? So
Yes.
you will get actually this type of scenario, this figure,
বুঝতে
when you
পারলাম।
join
Yes.
this, right? EFM, EFS align, and this has gone up. That's why there is a bend in the band like this.
Yes, sir.
Okay.
Yes.
Now you can see that without even applying any voltage, there is a built-in voltage here, built-in potential here, and also here, just like PN junction. There is a tilt in the oxide conduction band. That means there is a voltage drop across the oxide,
Yes,
and
sir.
there is a bend in the energy bands in the semiconductor. So that means there is a voltage across this region also. These are built-in potential, right?
Yes, sir.
Now, as I told you, the first thing you have to do in this scenario is forget about everything. The first thing you have to do is make the bands flat. So how can you make the bands flat? By applying a negative
So
voltage here with
equivalent
respect
voltage
to
of,
this.
yes, sir.
Okay.
Of
Apply a negative voltage on metal with respect to
that
semiconductor.
semiconductor.
And what will be the magnitude of that voltage?
মানে ইলেকট্রিক ফিল্ডটা হবে স্যার মাইনাস ই। ও ইজি স্যার, এই যে এটা মাইনাস এটা কিউ ফাই এম, মানে ফাই এম মাইনাস ফাই এস, স্যার ফাই এস মাইনাস ফাই এম।
Hmm. That means you have to apply phi ms voltage at the gate. Phi ms
Phi
is negative,
ms.
remember.
Yes, sir.
Okay. So when you apply phi ms voltage at the gate, flat band voltage VFB is phi ms. Their bands will become flat.
Yes, sir.
So now think about depletion or accumulation. You want to achieve accumulation. So what do you have to do? This voltage is already there. In addition to that, you apply a negative voltage here, positive voltage here. So what will happen?
So আরেকবার স্যার কাইন্ডলি স্যার আরেকবার একটু বলুন।
Negative voltage here, positive voltage here. Go up,
স্যার
down.
নেগেটিভ, তো স্ল্যান্টটা অন্যদিকে হবে স্যার। সো ইটস লাইক
This go downward.
উইল গো ডাউন। ইয়েস স্যার, হ্যাঁ।
So there will be accumulation here. Gap between
sir.
EIF will increase, accumulation here, right?
ইয়েস স্যার,
Depletion.
আগের মতন স্যার, নরমাল
Okay,
কেসে চলে
exactly similar to the ideal case.
ইয়েস
Depletion, you apply positive here. In addition to this, this is already there. Okay,
ইয়েস স্যার,
this is here to make this flat. Now you apply positive voltage, additional positive voltage here, negative voltage here. So what will happen? Go down, go up. So gap between EIF will decrease.
accumulation will occur.
Depletion. No.
Depletion will occur, sorry.
Depletion.
Yes.
You increase this voltage, this additional voltage, EI will go below EF, inversion. So everything else is similar to the ideal case. Okay.
Yes,
The
sir.
only difference is at the beginning you have to make the bands flat band voltage by applying this voltage.
Yes,
Understood?
Sir. Yes, sir.
And one interesting thing here, you can understand that this gap, in order to, the total band bending here is how much? Q phi ms.
Q phi ms. Yes, sir.
This total band bending. So the applied voltage, if you apply phi ms, this will go down. These energies will go down by phi ms. Phi ms. So this gap between the Fermi levels is QV, where V is phi ms, right?
So, sir, my Fermi levels will not be aligned, sir.
No.
When they are working like normal.
When they are flat, these energies levels are flat. Of course, Fermi levels are no longer aligned.
No longer.
And their gap is this Q into phi ms. You can understand. This is phi m, Q phi m. This is Q phi s. So this is the difference between these two.
So in the ideal cases, the Fermi levels were aligned at this stage.
Because phi m was equal to phi s.
Phi s, বুঝতে পেরেছি।
But here they are not aligned. In order to align this, you are applying this additional voltage.
Yes, sir.
Understood this?
Yes, sir.
And one other interesting thing here is, if the difference between phi m phi s is large, then it may happen that even without any application of any external voltage, there may be inversion.
Oh.
Phi ms. Phi ms is the total band bending. Phi ms may be greater than Q phi f. Q phi ms may be greater than Q phi f.
Yes, sir.
Okay. Just say observation. It may happen. So those are the things mentioned here. If we try to construct an equilibrium diagram with phi m negative, we find that the aligning EF, in aligning EF, we must include a tilt in the oxide conduction band, implying an electric field. They're talking about this tilt. Thus, the metal is positively charged and the semiconductor surface is negatively charged at equilibrium to accommodate the work function difference. Okay, so you can see if the bands bend like this, there are actually electrons. Electrons, not electrons, actually negative charge here and positive charge here. That will be there
Yes,
for
sir.
aligning the Fermi levels. Okay.
Yes, sir.
কোথায় গেল? As a result, the band bend down near the semiconductor surface. In fact, if phi m is sufficiently negative, sorry, phi ms is sufficiently negative, an inversion region can exist with no external voltage applied. To obtain the flat band condition pictured in figure cathode B 618B, that means this figure, we must apply a negative voltage to the metal, that means gate, which is VFB equal to phi ms. Understood?
Yes, sir.
Now, another effect. This is one non-ideality. Another non-ideality is interface charge. Interface charge is what? You remember we have a metal oxide semiconductor, uh, three layers actually composed together. So here we have oxide layer. Oxide layer is actually made on top of a silicon layer. This metal layer was not here during the fabrication. Initially, there was silicon, bare silicon layer. On top of the silicon layer, this oxide layer was grown by how? There is a chamber, reaction chamber enclosed, which is closed within highly pure. The environment there is highly pure, uh, because uh, highly pure means actually there is not no, I would say very little amount of contaminants present in that chamber. In that closed chamber, this silicon is placed, bare silicon, and oxygen is supplied. The temperature is raised. There may be some catalysts also to assist the reaction between oxygen and silicon. So the oxygen reacts with this silicon at the surface and forms the silicon dioxide layer. Okay, as time passes, more and more oxygen diffuses here, because you can understand, if you supply oxygen, uh, there will be diffusion from high concentration of oxygen to low concentration of oxygen, right? Oxygens will diffuse and will react with the silicon. So that's how, with passage of time, a layer of silicon dioxide will grow. And once the silicon dioxide layer is grown, then on top of that, this metal layer or N plus polysilicon layer is grown. Okay, that is how things are made. Now, when this silicon dioxide is grown on top of the silicon, because of some effects, additional charges, additional positive charges will accumulate here. Actually, there are four types of charges which can be created here, which are shown here. Mobile, QM is the mobile ionic charge. Q uh, OT is the oxide trap charge. QF is the oxide fixed charge, and QIT is interface trap charge. What are these? I am just explaining to you. In addition to the work function difference, the equilibrium mass structure is affected by charges in the insulator and at the semiconductor oxide interface. Okay. For example, alkali metal ions, Na, sodium ion, can be incorporated inadvertently, that means unintentionally, in the oxide during the growth or subsequent processing steps. I told you oxide is grown. So in the reaction chamber, probably one catalyst has something which contains sodium, or previous, or maybe the from the body of the reaction chamber, sodium ion may come. Since this sodium is a common contaminant, it is necessary to use extremely clean chemicals, water, gases, and processing environment to minimize its effects on the dielectric layer. The dielectric layer means oxide layer. Silicon ions introduce positive charges Qm in the oxide. So Qm, M is for mobile. Silicon, this sodium ions can to some extent move within the oxide layer in response to the applied electric field, applied voltage across the oxide layer. That's why mobile for M for mobile, QM. Which in turn introduce negative charge in the semiconductor. So if there is positive charge coming from sodium ions here, they will, through electrostatic attraction, will induce negative charge in the semiconductor, right? So even without doing anything, there is accumulation of, there is positive charge here, negative charge here. So there will be a potential difference here. There will be associated tilt in energy, in the energy band and also in the oxide conduction band. But that is not the only charge. There are also other charges. The effect of such positive ionic charge is in the oxide depends upon the number of ions involved and their distance from the semiconductor. So these ions may be close to the interface. In that case, their effect on the semiconductor will be more prominent. More charge will be induced, a negative charge will be induced here, or they may be away from the interface. On that case, their effect will be less prominent. And also the number of ions involved, that is also a criteria for more is the ions, more will be the effect on the semiconductors. The negative charge induced in the semiconductor is greater if sodium ions are nearer to the interface than if they are further away, which I have already told you. The effects on this ionic charge on the threshold voltage is complicated by the fact that sodium ions are relatively mobile in silicon dioxide. So as I told you, they can move a little bit, particularly at elevated temperature. At high temperature, their movement is increased and thus can drift in an applied electric field. So if you apply positive charge, negative charge here, positive volt, negative voltage, negative voltage here, these mobile ions can go in this direction. If you reverse the voltage, these mobile ions can go in this direction. So you can understand their effect on the semiconductor also changes as they move away or close to this interface, oxide semiconductor interface. Electric field. Obviously, a device with VT dependent on its past history of voltage bias is unacceptable. So previously, if you have applied plus minus, then the ions will be here. Now, if you withdraw the voltage, the ions will still remain here. So their effect will be more prominent here. In the following subsequent step, if you apply a voltage here, if you want to use this MOSFET, the threshold voltage of the MOSFET will depend on this position of the mobile charge, which actually came from the previous applied polarity of the applied voltage, right? The previously we applied plus minus, from there ions came here, and that is determining the threshold voltage. So this is unacceptable. Okay, that's what they are mentioning. Obviously, a device with VT dependent on its past history of voltage bias is unacceptable.
Also, sir, like one time if I use it, it will be more closer to the interface. If I use
Exactly.
it with the reverse voltage, it will be less. Okay.
Yeah. If you apply positive here, negative here, these will go away from the interface.
Yes, sir.
Then if
Effect
you
will be
withdraw
less.
this voltage, the charges will remain here. So now their effect is here on this is less.
Less, yes.
Okay, so when you want to use the MOS device later on, the threshold voltage will depend on that previous voltage you applied. Okay, that is the history.
Yes, sir.
Polarity of the previous voltage you applied. So this is unacceptable, which is why, fortunately, sodium contamination of oxide can be reduced to a tolerable level by proper curing processing. Okay, so if you can reduce this sodium ions sufficiently, then their effect will be almost negligible. The oxide also contains trapped charges Q OT due to imperfections in the silicon dioxide. So in the silicon dioxide layer, because of imperfection, there may be some charges. Imperfections means you can understand the variation from periodicity of the crystal. So there may be some imperfection. Because of that, there may be some oxide trapped charges, OT, oxide trapped charges. Those trapped charges are fixed, they cannot move. Okay, only this mobile charges can move, or mobile ionic charge. So that is another type of charge, oxide trapped charge. In addition to oxide charges, a set of positive charges arise from interface states at the silicon dioxide interface. That is QIT, interface trapped charges. This last one, QIT here. This result from the sudden termination of the semiconductor crystal lattice at the oxide interface. That means here at the interface, suddenly the semiconductor crystal structure is terminated, actually any surface of a crystal is can be viewed as a crystal defect. Why? Because at the surface, the periodicity of the crystal is violated, right? So
Yes,
any surface will have uh, uh, will can be considered as an imperfection, and they will have trap state. Remember, I told you uh, uh, imperfections introduce um, um, allowed energy states within the band gap, trap states, right? So associated with that, those trap states, there can be some charges, and those charges are those interface charges, QIT, uh, interface trap charges. Near the interface is a transition layer SiOX containing fixed charges QF. This is the fourth charge. QF is the fixed charge. What is that? When oxygen is reacting with silicon, remember this oxidation reaction will be allowed for a certain amount of time. That will depend on the desired thickness of the oxide layer. When the desired thickness is achieved, the supply of oxygen will be terminated. Now remember, oxygens were going diffusing and was reacting with silicon. Now uh, here at this interface layer, some silicon atoms were in the process of reacting with oxygen. Those silicon atoms becomes available, ionic, and they were expecting oxygen atoms, but suddenly the oxygen atoms supply is terminated. So what will happen? There will be some dangling bonds. Dangling bonds means unsatisfied bonds. Okay. So one silicon atom is supposed to bond with two oxygen, but uh, some silicon atoms will have less than two oxygens. Okay, X is two. Sorry, X is less than two. SiOX, X is less than two. So because of that, there will be some charge. Okay, that charge is called fixed charge, and that will remain at the interface at this surface. So as oxidation takes place in forming the SiO2 layer, silicon is removed from the surface and reacts with oxygen. As I told you, silicon from the surface reacts with the oxygen, and that becomes silicon dioxide. When the oxidation is stopped, some ionic silicon is left near the interface. These ions, along with uncompleted silicon bonds at the surface, result in a sheet of positive charge QF, this fixed charge near the interface. Okay, so these four types of charges are there because of impurities or imperfections. Understood? These are also shown here. Okay, this is QIT, interface trap charge. These are fixed charge at the, this is the interface. Okay, so this is QF, fixed charge. These are oxide trap charge, which are fixed, and there are some mobile charges, sodium ions. So it's difficult to actually consider these charges separately. So what will be done is these all charges will be combined into a single charge, QI, interface charge. And fortunately, we know that that charge is positive. You can see this is positive, sodium ion is positive, oxide trap charge is positive, this fixed charge is positive. So total charge is positive, and that is QI. So for simplicity, we can include the variety of oxide and interface charges as in an effective positive charge at the interface QI coulomb per centimeter square. Remember, all charge and capacitances are expressed in terms of per unit area. The effect of this charge is to induce an equivalent negative charge in the semiconductor. Thus, an additional component must be added to the flat band voltage. So, QI amount of charge is here, which is a combination of these four charges. And there is positive charge. So, positive charge here will induce negative charge here, right? So, this is equivalent to applying a positive voltage here and negative voltage here, which is equal to QI by CI. Since QI is present in this oxide or close to this oxide interface, so this QI can be obtained in terms of a voltage. This QI will cause a voltage drop across this structure, and that can be obtained by just dividing QI by CI. So QI by CI will be the voltage across this because of this QI. So you have to, and because of that voltage, there will be some band bending here. And in order to nullify that, remember you have to make the bands flat. In order to nullify that, you have to apply a opposite voltage here. That means negative here, positive here, negative voltage of the metal, which is in magnitude equal to QI by CI. Understood?
Yes, sir. But sir, এখন একটা question, sir.
Mhm.
Sir, in the above case, sir, ওই যে sir, যে ফার্স্টে যে এররটা হয় এই যে ফার্মি লেভেল অ্যালাইন না হওয়ার জন্য, ওখানে ইলেকট্রিক ফিল্ডটা এটার অপোজিট ছিল না স্যার? হ্যাঁ স্যার। তো এটা একটা একটাকে কাটাকাটি করে দেয় না?
We will not think about that. We will think that in order to compensate work function difference, we have to add this voltage.
Yes, sir.
In order to compensate the effect of interface charge, we have to add this voltage.
Okay, okay.
So the total voltage is this. Now they may cancel each other, they may add, they may subtract. We don't need to think.
Sir, why is there a negative sign here, sir?
Because
Before
negative voltage you have to apply. QI is positive.
positive. Okay, okay.
QI
okay,
is
okay. Yes,
positive.
yes. So
So
negative voltage.
QI will cause, the effect of QI is like positive voltage here, negative voltage here, QI by CI. So
Yes, sir.
in order to nullify the effect of that voltage, you have to apply a voltage of opposite polarity. Now negative here, positive here. So minus QI by CI voltage you have to apply.
Yes, sir.
Okay.
Yes, sir.
So phi ms you had to apply to nullify the effect of, to make the bands flat, instead of even if there is work function difference, and this is the voltage you have to apply to nullify the effect of the interface charge. So total
sir.
flat band voltage is this and this, phi ms minus QI by CI. Remember QI is positive, always positive. Phi ms is typically always positive. Understood?
Yes, sir.
So this VFB has to be added with that threshold voltage. This expression to get the threshold voltage in the real case, in the practical case. Okay, so threshold voltage will have four components. One component again is required to create the depletion layer. One component is required to make the, to achieve a strong inversion, twice phi f. Another component is required to make the bands flat because of work function difference. Okay, and another component is required to compensate the effect of interface charge.
Yes.
Understood?
Yes, sir.
Okay. Any question?
No.
Uh,